Okay, so last time we talked about the argument for the fact that there's a unique analytic subgroup corresponding to a Lie subalgebra of a group G, and there were a couple of loose points. In particular, I think that there was an error in our argument for this lemma. Okay, the lemma which said that if you take a subalgebra and you take a basis and define the notion of rational elements, then any element in the subgroup can be approximated by rational elements up to any precision that you want. Okay, so last time I guess Justin, right? You asked me if this argument worked. The argument that I gave actually proved that only one rational is required, and at that time it seemed that it did. But then when I went through this argument again, I realized that there was an error in the argument. I will explain this argument one more time and clarify where the error was, and then in fact the correct argument. And then there was another lemma whose proof I was not able to remember, so I'm going to give a kind of a concrete argument for that lemma. All right, and then we will switch to other things. All right, so now. So what is the argument for this lemma? So remember, you take a basis for a Lie subalgebra H of G, or rather GLNC. I mean, we can here assume that we have a Lie subalgebra of GLNC, and we have this decomposition as a subalgebra plus H plus a subspace, a complementary subspace, and on some small neighborhood, we have this bijection coming from the product of exponentials. So these are the assumptions. And now we take this basis and we say an element of the Lie algebra is rational if it's a rational combination of the basis elements. And then we wanted to show that any product of exponentials, any finitely many product of finitely many exponentials of the Lie algebra element can be written as a product of finitely many rational exponentials of rational guys and some exponential of something in the Lie algebra with a small size. Okay, so this was it. So what is the technique for the proof? The technique for the proof was so the first thing is that the first step is okay. The first step is that every element of H can be written as a product of exponentials with x small. So any e to the x, you can write it as e to the x over n to the power n, and choosing n sufficiently large, you can make x to the n as small as you want. Okay. Now we also have the BCH formula, which describes log of e to the x, e to the y. So this really we should think about as log of e to the x, e to the y. And this formula doesn't converge for all choices of x and y. You need some assumption on the convergence, okay? So we can assume that it converges, say, when absolute value of x and absolute value of y are small, okay? Here I chose epsilon depending on delta, but then this will lead to some problem in the inductive argument, because in the inductive argument, if I want to use an approximation here, if I want to say that I take the first n and I do the approximation and I want to make this guy small, then that epsilon will affect this one. Okay, so then the epsilon will depend on delta. Therefore, I've already chosen some epsilon and I've chosen the xi's, and then I cannot continue with this step anymore. So that was the error in the argument. But what is the correct argument? So the correct argument is that that the series on the right converges absolutely for. So I'll just upload a new version. For absolute value of x and absolute value of y less than epsilon for the norm of x and norm of y at the same time. Maybe I should write like less than epsilon and norm y less than epsilon, okay? And when a series converges absolutely, it becomes a smooth function of the variables. In particular, the series depends continuously on the choices of x and y. Okay, so now how does the inductive argument proceed? First, let's look at the case n equals 1. Even in the case n equals 1, I think I made a mistake. So for n equals 1, well, basically, I want to know that I can write e to the x, where x small, norm of x less than epsilon, can be approximated by rationals. Well, I wrote this as e to the r times e to the minus r times e to the x. That was okay. And then here I used the BCH formula. But then, well, what I said was that r can converge to 0, but r is actually converging to x. So what you have is like minus r star x. It is converging to minus x star x. But that is still 0, because if you look at the BCH formula, if I plug in y equals minus x, then I have a cancellation here, and all other brackets will be 0. In other words, this is another way of saying that, like in the BCH product, x star minus x is 0, just because e to the x times e to the minus x is the identity. Okay. All right. And now I don't run into any problem anymore, because I know that, well, if I have chosen the norm of x to be less than epsilon, when r gets close to minus x, well, I'm sorry, when r gets close to x, for some r, where did I, okay, here. So when r gets close to x, sufficiently close, then its norm will still be also less than epsilon. Okay, so the norm of r, which is the same as the norm of minus r, will both be less than epsilon. Okay, and now this product makes sense, because this was, we needed some convergence condition here, but that convergence condition is now satisfied. And now continuity also applies. The series is absolutely convergent in this range, and therefore it's continuous when r converges to x, when minus r goes to minus x, and the whole value, this is star, will converge to minus x star x, which is 0. Okay, therefore this exponent converges to 0. So that's the argument for the exponent converging to 0. All right. And now what about the inductive step? So now suppose that you have expressed some element of h as e to the x1 times e to the xn plus 1, with the xi's all having norm less than epsilon. Then by the induction hypothesis, I know that I can express the product of x1 to xn as some exponentials of rationals and something small. Now, I can use the induction hypothesis for every delta. Therefore, I can assume that this norm of x is less than any delta that I want. Okay? And as such, if the norm of xn plus 1 is less than delta, so here maybe here's a remark. If the norm of xn plus 1 is less than delta, is less than epsilon, sorry, which is our assumption, then for delta sufficiently small, we have, if norm of y is less than delta, then the norm of y star xn plus 1 is less than epsilon. That's because if you set y equal to 0, 0 star xn plus 1 is just xn plus 1, and that is just, that has norm less than epsilon. And the series is continuous in assuming that the arguments have norm less than epsilon. So if you choose delta less than epsilon and sufficiently small, then this should hold. This is just a consequence of continuity of this BCH series. Okay? Which means that I can do this star product here, x star xn plus 1, and it has norm less than epsilon. And now I can use the induction hypothesis for n equal to 1 only for this one term. It's now e to the something. That exponent has norm less than epsilon. So I am allowed to use the induction hypothesis. That was one thing that we missed. And when I use this, well, in n equal to 1 case, we get only one extra rational, but we already had other rationals coming before. So we can't do this with one rational, but with finite many rationals. Okay, so this is the correct argument. All right. So maybe I should erase this. Finally, we use, maybe I just write finally. we use n equal to 1 for e to the x star xn plus 1. And here we note that x star xn plus 1 has norm less than epsilon. Okay, because norm of this guy was less than epsilon, and you can get this small enough so that this product still has norm less than epsilon. It's something like, you have a point in a ball of radius epsilon, then you have a point which then if you take any point here, this would be the xn plus 1, then you take a sufficiently small neighborhood, a small ball around it that will fit into the epsilon ball still. Okay, that's just a variation of this simple property. Okay, so now for this lemma. What was this lemma? The next lemma was that, remember that I have this picture. I have chosen the H and the D and these small neighborhoods U and V on the H axis and the D axis, so that the exponential is a bijection there into G, and C. And now I want to look at the set of points in V with the property. Now remember, V is on the D axis, so that e to the y is in H. In other words, I want to know how many times I can jump from D into H. I want to show that this is not possible a lot. I explained this idea before. I want to show that I cannot have a one parameter subgroup that adds to H and becomes like extra part of the Lie algebra of capital H. All right. So what is the proof? So the proof is the following. So suppose I have a y in V. I can use the previous lemma. So for any y in V, so for any y in V, we write e to the y as a product of some rationals. The number of rationals that shows up depends on capital Y, of course, and something small. All right. Now I have to tell you how small I want this to be. I mean, I think I also, previously I called it delta. Maybe I call it delta here too. All right. So this is the delta that comes from the previous lemma. So, and we'll tell you how small I want delta momentarily. All right. Okay, so now remember again, the goal was to show that this set is countable. Okay, maybe I just write it like that, is countable. All right, I want to show that there's not the size of rational numbers element there. Now, any finite Cartesian product of rationals is this like of the set of rationals is countable. Okay, and the union of countable, many of them is like countable again. So if the cardinality of E, maybe this is redundant because I already this is in the statement, but anyway, but if I have like limited the space, so maybe I just write this. If E is not countable, which means it's bigger than countable, then we have y1 and y2 such that their rationals, and I do this approximation, are the same. In other words, e to the y1 is e to the r1, e to the rm, e to the x1, and e to the y2 is e to the r1, e to the rm, same ri's times e to the x2. Okay? So now, by isolating the product of the rationals, you can isolate this quantity in both, and from this you conclude that e to the x1 or e to the y1, e to the minus x1 minus x1, yeah. Did I write it correctly? E to the y1 x1. Right. So this is e to the y1, e to the minus x1 really is the product of these rationals. okay, which is equal to the e to the y2 e to the minus x2. Okay, so I multiply on the right hand side with e to the minus x1, so I get a cancellation with this one. Same here, I multiply by e to the minus x2, I get a cancellation, and the product of rationals are the same, so then I equate the two things. All right. Okay, so now what happens next is that I can now write, maybe I just continue like this. All right. So now I can write e to the y1 equals, or maybe e to the minus y1, that's a little bit better. I just invert both sides. I multiply on the right by e to the x1 and then invert both sides. So then I get e to the x1, e to the x2, or maybe to the minus x1, e to the x2, e to the minus y2. Okay, and now I want to be able to write star of x1 and x2. So I want to make sure that delta is such that if x and y are less than delta, then x star y converges. Converges absolutely. Okay, so I actually get another continuous function. Okay, so now, and not just that, but also it also belongs to that neighborhood U. Okay, so these are x and y in H. That neighborhood U that I have chosen, the neighborhood for which I have this bijectivity of exponential. All right, so when I look at here, so I have e to the minus x1 star x2, that is in U. Oops, why don't I change the color? Okay. Okay, so this is in U. And then what's left is e to the minus y2. The minus y2 is in V. And on this side, what do I have? I have this exponent which is in V, and I can think that I have something like e to the 0. Like 0 is in U also, all right? So now I was able to write some e to the something in U, e to the something in V as product of other things in U, other things in V, okay? But remember this picture and the choice of the neighborhoods U and V. Because the exponents lie in the corresponding open sets, this can only be true if the exponents are the same, okay? So as a consequence, we should have that minus y1 equals minus y2, and minus x1 star x2 equals 0. Okay, and already the first one implies that y1 equals y2, which is what we wanted. In other words, two distinct elements of the set E cannot correspond to the same list of rational elements. And since the number of rational elements is countable, the number of elements in E should be countable, because we got an injection from E into the set of finite sequences of rational numbers. Okay? Is it clear? Are you following? Okay, good. All right, so that's all I wanted to say about this. And now, last time we also talked about compact Lie groups. So remember that we wanted to classify compact connected abelian Lie groups. Okay. And the theorem is that any such group is a torus, which means it's isomorphic as a Lie group to a product of U1s, or rather the circle group. So geometrically, it looks like a multidimensional torus. Now, in order to proceed, we first define the concept of a discrete subgroup. A discrete subgroup of Rn is just a subgroup where the identity element is isolated, or equivalently any element is isolated, which means that the element has a neighborhood, open neighborhood, which doesn't contain any other element of the group. Okay, so this was the definition of a discrete subgroup. And it was natural to expect that the discrete subgroups of Rn are obtained by integer combinations of linearly independent vectors. And our goal was to prove this. And we kind of stopped after the first step. This is the lemma. So you suppose gamma is a discrete subgroup of Rn, a finite dimensional vector space over R, doesn't matter. Then there are linearly independent vectors in this space such that gamma is just a set of Z combination of those vectors. So this is the goal. Any questions? Is it clear? What do you want to prove? All right. Okay. All right. So now what was the idea? So how do we construct these vectors? Well, we started by this technique of choosing a vector of minimal length other than the zero vector. Okay. So suppose that, I mean, the first thing is that we can assume that in fact, V is spanned by gamma, because otherwise we could suppose that gamma is a subgroup of a subspace of V. So we can always assume that V is spanned by gamma. All right, that makes life a little bit simpler, as you will see. And then now we choose some element like gamma naught in this group, in this discrete group, which has minimal length, but that element is different from the identity, from the zero element being the identity, okay? And then what we do is we consider the orthogonal complement to the subspace spanned by this element. And then, well, it would have been nice if gamma was like what we generated by its intersection with this subspace and gamma naught, but that's not the case. It's hard to, it's like it's very rare for this to happen. But then we can do the following trick. We can do orthogonal projection of elements of gamma onto the subspace. So I represent these orthogonal projections by PW gammas for any gamma in capital gamma. All right. Okay, so remember, W is just this orthogonal complement of the orthogonal subspace to gamma naught and so on. Okay. So the first thing is I want to show that this gamma prime, well, clearly this is a subgroup because this map is a linear map. This PW is a linear map. So this gamma prime, you know, is a subgroup. All right. But we need to show that it's discrete. All right. So suppose it's not discrete. So then what happens if it's not discrete? So this means that there's a sequence of elements that converges to the zero element. So if, oops, I have to use white. Okay. Suppose you have this sequence gamma prime n which are elements of this projected subgroup gamma prime. And gamma prime n converges to zero. Suppose that such a thing exists. Did I stop sharing? No. Okay. So then what we can do is, well, we know that these gamma primes are in the projections of gamma. So we can look at their some pre-images. All right. So now we choose gamma n's in gamma such that the projection of gamma n is gamma n prime. So where are the gamma n primes? So they are basically here. So maybe I'd represent them here. They're going to zero. This is gamma 1 prime. This is gamma 2 prime, and so on. And now I pick some pre-images. These are like gamma 1 double prime. Did I call them gamma double primes? Well, just gamma, like no double primes yet. Okay. Gamma 1. 2 gamma 3. Okay. So these preimages, there is no reason yet to expect that these preimages converge to 0. They can go to infinity even though their projections go to 0. Okay. So we're not done yet, but what we can do is now we can project these guys on the other axis. Okay. So now what we do is we set gamma n double prime to be the projection on the subspace R gamma naught is spanned by gamma naught of the gamma n's. Okay, so we have this subspace. As you can see, it's the subspace that goes through this vector. And I'd like to project these guys also on this subspace. So how does each projection look like? Let me draw another picture here. So this is that subspace spanned by this gamma naught. So we have these vectors like gamma naught and then 2 gamma naught. And in general, we have like n gamma naught, n plus 1 gamma naught. Okay. And each of these projections, it will lie between 2 successive integers. Maybe it's better if I change my indices. Maybe I just put the projection here. Maybe I just draw another picture here. Okay. Oops. Wrong page. So this is say like gamma n, and here is gamma n double prime, the projection of gamma n onto the subspace. It will lie between n gamma naught and n plus 1 gamma naught for some n. And it will be closer to one of these two guys. And the distance will be 1/2 of gamma naught anyway.
At most.
Okay. So then we can assume, so we can choose n in Z such that gamma n prime. So maybe for any, maybe I write for any n, we can choose capital N depending on this little n, such that the distance between gamma n double prime and n gamma naught is less than 1/2. Actually, I cannot have it strict, but I should have like this. Okay. It could be right in the middle, so then it will not be strict. Right. So now let us look at the distance between gamma n and n gamma naught. So what is the point? So the point is that I want to argue that I want to argue that for these gamma n's, at some point, if I subtract a suitable integer multiple of gamma naught, I will get a vector shorter than gamma naught. In other words, I want to reach a contradiction with gamma naught being the shortest non-zero guy. Okay. We know that these gamma n's, they're not in this subspace. Okay. So what is happening is that, so we have, so this is equal to, so now, well, we have the following situation. So we have, maybe I should draw a picture. Or maybe I could complete this picture. Should I draw a new picture? Maybe I should draw a new picture. So we have this gamma n, and there was a projection of gamma n here. This is this gamma n prime, and then we had this other thing. So we had this, and this is the origin, and this is this gamma n double prime. So now you can use the Pythagorean theorem to describe the length of gamma n minus n gamma naught. Okay. So you can write this as length of gamma n minus its projection on R gamma naught okay squared. Okay, maybe I should, okay, I don't know where I should write, but maybe, okay, maybe I should write in the next line. So I have gamma n minus gamma n double prime, where gamma n double prime was the projection. So this is the gamma, this is the projection on R gamma naught of gamma n squared plus gamma n double prime minus n gamma naught squared. So what I'm doing, actually, maybe I should correct my picture. So I am looking at this. So this is n gamma naught, and I'm looking at this distance. Okay, and I'm now and now I'm using the Pythagorean theorem in this triangle. All right. Now if I can just scroll up, okay, I can continue. So what I have, so now, but of course, I have to raise it to the power of 1/2. The square of this length equals the sum of the squares of the sides of the, like, I mean, the square of the hypotenuse is equal to the squares of the sum of squares of the sides. But I have to raise it to the power of 1/2 if I'm interested in that length. Okay, all is good. You guys are able to follow, right? Okay. And so now, what I can see is that, well, the first quantity, this is gamma n minus gamma n double prime. And, well, this is at most 1/2. Where did I write it? Okay. Well, okay, so I can choose, here's the point. So I can choose, so this is really the projection, right? So this is, okay, maybe I should write one more line. Remember, I'm subtracting the projection onto this gamma naught direction. So what is left is the projection on the orthogonal space, okay? So this is really a projection of W on W of gamma naught squared plus the other quantity. And now for n large, this goes to 0. So I can assume for n large, this is like less than, I don't know, 1/2 gamma naught. Okay. So for n large. So the first one is at most 1/2 gamma naught squared. And the other one, well, by the choice of n, that is how it is. Okay. So it's at most 1/2 gamma naught squared. So you have to the power 1/2. So the sum of these is just like gamma naught squared. So you end up with like gamma naught squared to the power 1/2, which is gamma naught, length of gamma naught. Okay, so what is the consequence? So I found some element of gamma, which is this little gamma n minus n times gamma naught, which is non-zero, and it has a length shorter than that. Okay, so now length gamma n, and now, okay, so gamma, so this contradicts. Maybe I should write this contradicts. All right, so now let's try to prove our theorem. Okay, I'm not done. Okay, I didn't finish the proof of this. Okay, so we just proved that. So what did we prove in this step? We proved that this gamma prime is discrete. Okay, but I mean, we're basically almost done. We know that these projections, they live in some subspace of codimension 1. So by the induction hypothesis, by induction on the dimension, you can assume that you have some spanning set, and now you can lift this spanning set. So here's the last step. So the last step, step 3. By induction on the dimension, we know that Gamma prime is Z times, maybe I write like W1 plus ZW, maybe what's the index? Maybe I should just R for W1, WR in W, this codimension 1 subspace of V, linearly independent. Okay, so now we choose gamma 1 tilde up to gamma R tilde in gamma such that their projections are these WIs. Okay, note that these guys, I mean, they're also elements of gamma prime because if you put 1, 0, 0, 0 as the coefficient, you get W1. So these guys are also in W1. So they're also in W1. Okay, sure, right. Also in gamma prime. All right. So this is 4 between 1 and on. Okay. And now, given any gamma in gamma, well, how do you write gamma as a linear combination of the gamma I tildes and the gamma 0? This is what I want to do. I want to show that gamma 0 and the gamma I tildes form the linearly independent sets. The linear independent set of vectors that span gamma. Okay, so take some element of gamma. So what I know that PW gamma can be written as a linear combination of the W's. So this is equal to like M1 gamma, M1 W1 plus MRWR, where the MIs are integers. And then so this means that gamma minus sigma mi gamma I tilde, it's a vector that's orthogonal to W, right? Because PW of gamma minus PW of this will be just the difference of the two sides of this relation. So it's 0. Okay. And this means that this PW gamma, this means that this gamma minus this sum, which is the element of capital gamma, is in the span of gamma naught. So gamma minus sigma mi gamma I tilde, maybe I should put all these indices, is in W perp which is R gamma naught. All right. But now, so this element is in gamma. And now, again, you can use the same argument. If this guy is not an integer multiple of gamma naught, then you can subtract an integer multiple so that you're left with some like a scalar between 0 and 1 multiplied by gamma. Okay. And we have gamma, maybe I call this like gamma tilde. And we have gamma tilde is like R gamma naught for some R in R. And if R is not an integer, then gamma tilde minus the floor of R times gamma naught is in gamma and is of the form gamma naught minus, I'm sorry, is of the form C times gamma naught, where like C has absolute value less than 1, bigger than 0, which contradicts again the minimality of the norm of gamma naught. Okay? So this means, consequently, R is in Z, and therefore gamma is sigma mi gamma I tilde plus R gamma naught, which is in the Z gamma 1 tilde plus Z gamma R tilde plus Z gamma naught. Okay? All right, so now we prove this lemma, that every discrete subgroup of Rn is an integer combination of a set of linearly independent vectors. Now let's come back to the proof of this theorem, which we wanted to prove. The theorem is that every compact connected abelian Lie group is just a torus. Okay, so how do we prove this theorem? So maybe I just write the theorem again. Okay, so theorem. Every compact connected. So now, okay, maybe it's now a good time to actually go to the corrected slides for the day. So last time I forgot to switch to my slides to lecture 18, and then I was in the middle of a proof, so now I'm continuing here. So, okay, so now let's come back to here, the slide for lecture 19. So the theorem is that every compact connected abelian Lie group is a torus. So how do we prove this theorem? So the idea is take advantage of the exponential map. Okay. Now, since the group is abelian, what is its Lie algebra? What can we say about its Lie algebra? It's an abelian Lie algebra, exactly. And therefore, so if T is the group in this, I mean, the group in the theorem, and this fracture T is the Lie algebra of T, then T is abelian. And now let's see what this means about the exponential map. What does it say about the exponential map? So, pardon? Well, it's its definition, but I mean, okay, so this is the map that takes x to e to the x, but what does T being abelian say about the exponential map? Well, if you take x and y in the Lie algebra, then what can you say about e to the x, e to the y in this case? Yeah?
Equal to e to the y to the x.
Yeah, or you could say even more that this is just e to the x plus y, because you can think about x and y, they're in GLNC, and they commute with each other, okay? For commuting matrices, e to the like product of exponentials equals exponential, like exponential of the sum. Okay? That's because when you write the series, you see, when you write the series, sigma x to the n over n factorial multiplied by sigma y to the n over n factorial, whatever, n to the n factorial. Just like ordinary series of numbers, this is equal to sigma x plus y to the n over n factorial. If you expand, the terms are the same. This wouldn't work if x and y wouldn't commute, because here you would have things like xy and yx, which are not the same, so you couldn't sort them out. But when x and y commute, this is all okay. Which means, okay, now that we have this relation, this means that, in fact, the exponential map is a Lie group homomorphism. Okay? It's continuous for sure. And it's a group homomorphism from Lie algebra T. Lie algebra T considered as a vector space, which is also a group, to T. And also, remember that some time ago, we proved that the exponential map for abelian Lie algebras is surjective. You remember when we proved this some time ago? I forget the lecture number, but it's somewhere. So, like, if you should find the reference. When we talked about the Lie algebra of a Lie group, we proved surjectivity of the exponential map. And the argument was that okay, and now I forget the argument, but we certainly did prove it. So also, since T is abelian, X is a surjection. Okay. You remember anything from the proof? Let me see if I can remember. Okay, I don't remember it, but I'm sure we did it. Okay, like find the proof. It's somewhere in the notes. All right, so now what this means is, so now we have this Lie group homomorphism, and on the other hand, the exponential map, as we know, it's a diffeomorphism near zero. So what we have is a Lie group homomorphism which near zero doesn't, it near zero is a bijection, which means that, in fact, the kernel of this map cannot have a sequence of elements converging to zero. Okay, so since the exponential map anyway is a bijection on some neighborhoods, of course, near zero in the Lie algebra, it follows that the kernel of the exponential map is a discrete subgroup of this vector space, hence abelian Lie group T. All right. All right. So now, by the first isomorphism theorem, whatever. So so maybe I just call it gamma. So now, because of surjectivity of this, we have this isomorphism. This is first isomorphism theorem, right? Okay. So we are able to describe the compact abelian group T as a quotient of gamma, as a quotient of the vector space T by its discrete subgroup. Okay. So now, what is this quotient? Well, what you can do is you could look at this subgroup gamma. It might not span T, but if it doesn't, then you just take some complement. So maybe I just draw a picture. So this would be gamma, maybe, which looks like a lattice, but maybe it's an R3. So you can take some complement, maybe D, And what it spans is maybe I'll call this W. So then T is, as a vector space, it is D direct sum W. And when I factor by gamma, only the factorization takes place in W, because these like doesn't intersect the subgroup. The intersection is just the zero element. Okay. So now this D would be some Rm anyway. And when you factor Rn by this discrete subgroup, what do you see? So you basically see this region in the sense that this side and this side of this parallelogram, they're identified. Okay. In other words, these 2 points in this quotient, they correspond to the same, because the points here are obtained from the points here by some translation by elements of the group gamma. And same here, this side and this side are identified. So this looks like you have taken this parallelogram and you have glued the opposite sides. So this means that you actually end up with a torus. And this happens in the multidimensional case. If you replace this parallelogram by a parallelepiped, that's again what happens. It's a little bit hard to imagine, but that's what happens. All right. So then this quotient W over gamma, it's really a product of circles. The number of circles being the same as the number of generators of this group gamma. But we know that T is compact. So we shouldn't have any copies of R, because that will make the group non-compact. So M should be 0, and T over gamma is just isomorphic to some product of circles. Okay? Is it all good? So I want to give you some outlook before I switch subject. So what do we need these abelian connected Lie groups for? So they allow us to actually characterize, or rather completely classify, all compact Lie groups. So what is the idea? So the idea is that if you take a compact Lie group, well, maybe I should say compact connected, because anyway, if you remove connectedness, any finite group will be a compact Lie group. So this makes the problem kind of pathological. So let's consider a compact connected Lie group. So then you can always choose abelian subgroups of this, or rather you can choose maximal abelian subgroups of T. Okay, so this T would be a maximal abelian, maybe connected. Okay. G. Okay. Then in fact, you can show that any 2 such subgroups are conjugate, which means that they're related by some conjugation by some element of G. If T and T prime are 2 such subgroups T, which we would like to call them tori, as we decided earlier. So these 2 tori are conjugate by some element of G. Okay. And then what you do is you look at the action by the adjoint representation of such a torus on the Lie algebra of G. So you look at the Lie algebra of G, and of course there's the Lie algebra of T sitting in here, and you look at the adjoint action of T on G, and you can see that if you complexify this, then in fact this action is by a family of diagonalizable matrices. So action of T so this leads to a decomposition of this complexification as the complexification of TC and some eigenspaces. Okay, these are the joint eigenspaces of the commuting family of linear transformations coming from this torus. Okay, and this leads to the theory of root systems. So you can show that in fact what you get as GC is a Lie algebra of semi-simple type. Okay, and there's a full classification of semi-simple Lie algebras, and in each the classification type there is exactly one compact Lie algebra of the isomorphism. So basically, you get a full combinatorial description of all compact connected Lie groups. So examples that you have seen are these unitary groups, and then the orthogonal group, the compact orthogonal group over R, and then there's also a compact version for the SP, which we discussed. And there are some exceptional ones, and that's basically it. So this is a full classification of all compact Lie groups, which is one of the fundamental results in algebra in some sense. This is like one of the most important results in algebra, where you have a complete classification of these compact Lie groups, and this allows you to develop a theory uniformly for Lie algebras or Lie groups, like for the reductive class and so on. Okay, any questions? Yeah.
How about the whole like simply connected cover story? Like how much information is lost there? Because the Lie algebras to classify the Lie groups.
Okay, so so if you take a connected, a compact connected abelian, if it's abelian, then the simply connected cover is always Rn. Okay, so all these compact groups have like a simply connected cover, which is non-compact, but it's still a matrix Lie group. And if you take a compact Lie group which has no center, then in principle, you can go to a finite cover, which is universal cover. You don't have to go to something infinite cover. You don't have to go to something non-compact. And you can figure out which cover you should go by looking at this root system and like this, or some more precisely on the index of the weight lattice or and so on. So something about the weight lattice and root lattice, some information from there will tell you that. So some number that you can compute from this combinatorial structure that I described, how one can associate the root systems. Yeah, and then the other thing is that you can always write any compact Lie group as a direct sum of a centerless compact Lie group and the center. Okay, as a direct product or something like a direct product. Okay, that's not exactly correct, but maybe I should say as a Cartesian product of something which has discrete center and something which is just copies of tori. Okay, so you have so therefore you can reduce the analysis of all compact Lie groups to the case of Lie groups with discrete center. Yeah, and in any class of discrete center, if you factor the group by the center, you will get a centerless compact Lie group. That's the adjoint type. So the picture of the covers is that there's something sitting at the bottom of this covering. This is called the adjoint group, and something sitting at the top, the simply connected. And in the compact world, in the case of compact compact Lie groups with discrete center, basically this is a finite cover map. Examples would be, for example, we had this SU2, and here we had the SO3. Okay, so this was a double covering. And this guy has no center, and this guy has a center which is plus minus 1. But in general, there could be more groups in between. But everything from this can be understood from this root data. Okay, any questions? Yeah.
When the root system is equal to the center of the Lie algebra?
I didn't explain what the root system is. The root system is this combinatorial information, this weight decomposition. So from this and then something else called the weight lattice and so on, by comparing the index of some subgroup inside some another group subgroup, you can understand the size of the center. Okay, so yeah, so basically you have to, so okay. This will drift us away a little bit, but so you start with this compact Lie group, you look at this, all the modules for this, all the representations, all right? And then remember that I have this this root decomposition with lambdas coming from the dual of the CC star. The representations are also parameterized by mu's inside TC star. This is something similar to what we saw for the case of SL2C, right? We talked about representations. Oh, we talked SU2, doesn't matter. So the representations of SU2, right? So they were parameterized by these integers. You should think about these integers as linear functionals on a one-dimensional Cartan subalgebra, on the subalgebra of matrices of the form IT 0, 0 minus IT. Okay? And so now you see that we get a discrete subgroup, right? And in this case, the adjoint representation will correspond to the number 2. Okay? Number 1 corresponds to the representation on C2, and the adjoint representation corresponds to the number 2. And so now you see that the root lattice has index 2 in the weight lattice, right? Because you know, the weight lattice is generated by this 1. It's like, if you think about a subset of the real line, it generates by 1, whereas the root lattice is generated by the highest set of the adjoint, which is the number 2. The index is 2, and therefore the center of this has size 2. Okay, so that's how one does it. In general, one has to compute the index of the weight lattice for the corresponding isogeny class inside. I'm sorry, the other way around. You compute the index of the root lattice inside the weight lattice for this isogeny class. For the adjoint one, the weight lattice and the root lattice are the same, and this index will be just 1, and therefore, like, equivalently, the adjoint group has no center. Yeah. But there's a very beautiful picture. So I mean, pretty much any question in this world has a nice answer, either discovered or undiscovered. But yes, there is a nice answer. Okay. Okay, so now let us continue. I want to kind of move away completely from this topic and start talking about the notion of a Poisson Lie group. So this is one thing I promised. So to motivate this, let me tell you how Lie algebras can come about in calculus, right? So in order to do so, let me remind you of the concept of a vector field. So what is a vector field? Suppose you have some domain in Rn, and to each point you have associated a vector. So for any point P here, you have associated some vector, but you want to assume that the vectors vary continuously as P varies, right? So this XP depends on P continuously or even differentiable, like as nice as possible, okay? This is calculus, right? In calculus, functions are very nice. So now let me give the definition, a formal definition. So a vector field. Okay, so now what is a vector field? A vector field on UN, on U, which is a subspace, like an open subset of Rn, is C infinity map like X that goes from U to Rn. So it assigns to any point a vector in Rn. And this definition, I suppose, is familiar. Hopefully, I can assume this definition. Yes, they are the same, exactly, because the vectors are supposed to lie in the same space. Yeah, right. Yeah. Okay. Right. In fact, I mean, the main point is that the vectors should lie in the tangent space at P, But since this is an open domain in Rn, its dimension is n, and the tangent space is also n dimension. Yeah, so that's the idea. Okay. So now, so this is familiar, this definition, hopefully. All right. So now we can also talk about the flow of a vector field. And what does that mean? That means that if you put a particle at point P, then the particle can start moving around according to the velocity that is given by the vector at the point. So its velocity at P is xp, and when it moves at any point, its velocity vector is the vector at that point. Okay? And this movement is called the flow of the vector field. Again, the concept that I hope that you had seen somehow in calculus, maybe in some different language, but anyway, the idea is what it is. So the flow of x is a map which I'll denote by phi x. This time it's a map that goes from the set u times some time interval into u, so epsilon is some positive number, such that well, the velocity is just a derivative, right? The velocity of the movement, I should put upper t, upper x, sorry, lower t, at any point, maybe I should write. Yeah. Equal to 0 is just xp. So okay, sorry. Here I didn't write it correctly. I should write it as okay. I didn't write it correctly. Sorry. So this is at any t plus okay. T0, I should put T0 here. And here I should put x of phi T0x. Okay. So the velocity of the movement at any time is just the vector that is attached to the point where the movement is at that time. Okay? Is it clear? And now associated, okay, now, okay, unfortunately, we ran out of time more or less. So maybe I should just say that here I am simplifying life a bit because, I mean, technically one cannot assume that the flow of the movement is defined everywhere for a certain time interval, because it's possible that, say, for points near the boundary, after a short time, they will escape out. In other words, the flow basically goes to infinity, okay? Therefore, I cannot assume that for every point, I have a epsilon uniform time interval where the flow is defined. But sometimes it happens, and for simplicity of the presentation, I make this assumption. I can always, you know, let the time interval depend on the initial point, and everything will go through fine, because everything we need to do is some local argument. But for simplicity, I describe the flow as such. I could have also chosen the real line, but that would have been a little bit too much to assume that the flow exists for all real values, for all time values. Okay. All right. So what we want to do is we want to now look at the derivative, directional derivative of a function with respect to a vector field. And then we will see that for flows of two different vector fields, the two flows do not shift places, which means if you go according to the first flow and then the second flow, the result might be different from going from the second flow first and then the first flow. So now you want to somehow measure how different they are. Like in other words, how far from each other are two flows. And in order to measure that, you define a concept of the Lie derivative, basically. And using the Lie derivative, you will actually see that you get a commutator operator on the vector fields, which gives you a Lie algebra. So that's one of the origins of the idea of a Lie algebra and Lie group. Okay. So I'll talk about this next time, and then I'll tell you how this connects to the concept of a Poisson Lie group and so on. That will be kind of our first venture into the realm of quantization. And if there's enough time, I'll talk about another way of quantizing things, which is kind of integrating this idea of Poisson Lie groups. So we have 4 more lectures, and hopefully in the next 4 lectures, 4 more, right? Okay. Yeah, hopefully in the next 4 lectures, I'll talk a little bit about these things.